Hey Geometry, we're still rolling along with our robot, and the robot's helping us discuss lines in the coordinate plane with a little bit of fun. So let's just get to this lesson. The first two numbers, or the first two problems in your opening exercise, are a review of writing equations for lines given points and slopes. We reviewed it a little bit in class, so you should be able to do this one. So I would like you to try these on your own. I'm going to push pause and work through them, but if you could please push pause and try to get these on your own, seeing how you just reviewed it a few days ago. Okay, I used the slope-intercept form for both of these. First, you're given the slope here and a point. I use just y equals mx plus b. 0 is x, negative 5 is y. Plug them in. So y equals mx plus b. Solve for b, because we don't know where this line crosses the y-axis. And b is the y-intercept. So b equals negative 5. Plug it back into your formula, and you're done. Next one, we don't know slope, but we have 2 points, and we can always calculate slope given 2 points. So change in y over change in x gives me a slope of 4/3. Then I just grabbed one of these points and used the slope-intercept form again, xy. So y equals mx plus b. Solve for b. I got b equals 5/3. We can do this a different way, though. Let's get some space here. I can use what's called the point-slope form, which is going to be y minus y1 equals mx minus x1. Again, just pick one of the points and use it. So y minus 3 equals m x minus 1. That can also be an answer. Okay, if you simplified that equation, you would get the same answer here. Trust me. All right, so exploratory challenge. We are going to work through determining an equation of a line perpendicular to a given line. That's what we're learning today through a fun little exercise with a robot. So let's read through this. A search robot is sweeping through a flat plane in search of the homing beacon that is emitting a signal. A homing beacon is a tracking device that sends out signals to identify the location. Programmers have set up a coordinate system so that their location is the origin. The positive x-axis is the direction east, and the positive y-axis is the direction north. The robot is currently 600 units south of the programmer's location and is moving in an approximate northeast direction along a line given here. Along this line, the robot hears the loudest ping at the point 400, 600. It detects this ping coming from approximately a southeast direction. The programmers have the robot return to the point 400, 600. What is the equation of the path the robot should take from here to reach the beacon? Whew! Begin by sketching the location of the programmers and the path traveled by the robot on graph paper. Then shade the general direction the ping is coming from. I need graph paper. All right. So here is where the robot started, traveled along this line, travel. All those black dots you see are just me marking out the slope so that I could draw the line a little bit easier. And then this point up here is where the robot heard the ping from the beacon the strongest or the loudest. So the previous slide said begin by sketching the location of the programmers and the path traveled by the robot on graph paper. Then shade the general direction the ping is coming from. Going back, it says that the program has set up a coordinate system, so their location's the origin. That's where they are. Their location's the origin. The positive x-axis is east, y is north. So the robot was 600 units south of the programmer's location and moving in the linear direction. Cool? All right, so where's the ping coming from? right? If it's moving along this direction, the loudest ping is going to be when the beacon is a certain distance away. Okay, let me see if I can help out. Let's get a new slide. All right, you guys are going to see my artistic abilities now. I'm standing on a sidewalk. That's a sidewalk. I'm standing on the sidewalk. That's my curly hair. And obviously sidewalks are on streets. So I've got a car coming down the street. That's a beautiful car. Coming down the street, and it is playing some loud music. Super duper loud. So I can hear the music. I can hear it a little bit. You know, little bits. That music's coming to my ear. Okay, but when the car is closest to me is when I can hear the music the loudest. Need some wheels. My car drawing abilities are getting worse. That looks like a truck as I draw. So the music is the loudest when this car is closest to me. And we learned a long time ago in geometry, the car is closest to me. Oops. Oh, goodness. The distance is the shortest. The distance between the car the distance between me and the car is the shortest when the car is perpendicular to me. That's what I'm trying to get to. Perpendicular. So if I drew the road as a straight line, the distance between the car and me is the shortest when the car is perpendicular to me at a right angle. So this distance is the shortest. Make sense? Awesome. So if we relate that back to this problem, the loudest ping was heard at 400, 600. That means the beacon is somewhere on a path that is perpendicular to the path the robot is on. So the robot is currently on the path y equals 3x minus 600. So we need to know what path the robot needs to be on to find the beacon. The beacon is somewhere on that path. So if we can find the line perpendicular to the path of the robot that passes through 400, 600. Now the challenge here is how do we find the equation of this line, right? We need to find the equation of a line perpendicular to y equals 3x minus 600 that passes through this ordered pair. Make sense? So we know the slope of the robot. The slope of the robot is 3. What do we know about slopes of perpendicular lines? Slopes of perpendicular lines are the opposite sign and the reciprocal fraction. So that's going to be the slope of the line that the beacon is on, right? Oh goodness, that's hilarious. Almost. That's better. So the perpendicular slope is always the opposite sign and reciprocal fraction, right? So we can come up with an equation pretty simply. We can use either the point-slope formula or the slope-intercept form. I'm going to go ahead and use the point-slope formula. So I've got x and y. So y minus 600 equals negative 1/3 x minus 400. That right there is the equation of the line that's perpendicular to the robot that passes through point 400, 600, right? So our original path of the robot, the slope was 3/1 or 300 over 100 to make it easier. So for every 300 I go up, I go over 100. 300 up, over 100. 300 up, over 100. Once I get to the ordered pair, 400, 600, that's when I need to go perpendicular. So now I'm going to go, let's do this, negative 100 over 300. I'm going to go down 100, positive 300, down 100, positive 300, down 100, positive 300. And I get a line perpendicular to my original line. That's how your perpendicular slope works. Opposite sign and reciprocal, right? So I hope that helps you figure out how to write equations of lines that are perpendicular using the point-slope formula, which is probably the easiest one. So I've got the point and a slope. I just plug it into my point-slope formula, or I could use the slope-intercept form and come up with the equation for a line. All right, let's move on. Example, the line segment connecting 3,7 to 10,1 is rotated 90 degrees about the point 3,7. So plot the segment. Let's plot that segment. So I plotted the segment. We're rotating clockwise 90 degrees, so we're going this way. We're rotating about this point. So where will the rotated endpoint land? I really need all the quadrants of my graph. So if we're rotating about there, that means this is going to rotate. My point should actually land somewhere in the 3rd quadrant. Okay, that's what I'm guessing, but we'll know for sure here in a little bit. But it's somewhere in this direction, right? Because that's going to be a right angle. So I'm actually going to build a right triangle about this segment with some sound effects. There's my right triangle. That helps me know how I'm going to rotate it. So if I rotate it 90 degrees, I'm going to go, let's see, this leg right here is 1, 2, 3, 4, 5, 6. I'm going to go 1, 2, 3, 4, 5, 6. Tragic that I didn't put the right graph on here. So that's 6 units and that's 6 units. Here I've got 1, 2, 3, 4, 5, 6, 7 units. So I'm going to go down 1, 2, 3, 4, 5, 6, 7 units. And that's where my point is going to be. And that is actually at negative 1, 2, 3, 0. Negative 3, comma 0. Just using those right triangles, a lot easier to figure out. I mean, the slope of this line right here is rise over run, so I'm going up 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. I'm going to erase that now. Oops. My slope, original slope, is a rise of 6, a run of negative 7. So my slope here, my perpendicular slope, is positive 7 over 6, so a rise of 7, a run of 6, which totally makes sense, right? Okay, now it says rotate the original segment 90 degrees counterclockwise. So we're still rotating about this point, but we're rotating in that direction. So instead I'm going to go this direction 6 and up 7. And there's my new point with my new triangle. Okay, I have the same hypotenuse. My hypotenuse has not changed. My slope is just opposite reciprocal. So here the slope is negative 6/7, and here my slope is 7 over 6. How can I get my point, though, without calculating it? Say I didn't want to graph this whole thing. What would my point be? So if I look at my original point, we started out with an ordered pair of 3/7, and we rotated it. Our line segment has a slope of 7/6. This is going to be my change in y over my change in x. So I really can add 7 to my y and 6 to my x to get a new ordered pair of 9/14. Just another way to figure it out without actually drawing the rotation, right? And it works here. If my original point was 3, 7, I'm subtracting 6 to get negative 3 and subtracting 7 to get 0. I get my new ordered pair, right? Pretty cool, huh? All right, let's look at something else. So here we have point A and point B. At first, we're going to describe the location of AB after a 90-degree counterclockwise rotation about the origin. Here's what's important. It's about the origin. Draw a rough sketch to justify your answer. So my rough sketch, I'm through the origin. I want my cool triangle, right? So if we're doing 90 degrees that way, I'm going to want this to be here. Roughly, right? That's pretty rough. This is a direction of A, or a distance of A, and a distance of B, because it's X and Y. So now my direction of A is that way, and my direction of B is here. So I'm actually going up A and negative B. Let me highlight that. Positive A, negative B. But they've sort of flipped directions, right? Now I'm going in the Y direction and the X direction. Here I went X, Y. So we definitely have an A, B, an X, Y. But now here I have Y, X. So let's do this. I need different colors here. So Y and X, because that's my Y-axis, and that is horizontal, which is X. So my value is actually going to be negative B, comma, A. So a 90 degrees counterclockwise rotation will give us negative B, comma, A. And that's my rough sketch. If the rotation was clockwise about the origin, what is the rotated location of AB in terms of A and B? Hold on. So here, I needed to get the graph in here, sorry. If the rotation was clockwise about the origin, what is the rotated location of AB in terms of A and B? So the original location, I've got AB is XY. I rotated it 90 degrees clockwise. And you see that my A distance, my A measurement is now the negative Y, and my B is now the positive X. So we definitely need to go B negative A. Cool? Sort of fun. We rotated it. So what's the slope of the line through the origin and AB? The slope is going to be change in Y over change in X. What is the slope of the perpendicular line through the origin? That would be the part B that we did, where the slope is change in Y over change in X. Cool. So what do you notice about the relationship between the slope of the line through the origin and AB and the slope of the perpendicular line? They are opposite reciprocals of each other. If you multiply them together, I think we had B over A times negative A over B. Well, let's not do that. Let's just multiply across and see what happens. So I'm multiplying with fractions. Remember, you just multiply across. We get negative AB over AB. Okay, the product of them is negative 1. Cool? Cool. That's actually it for today. We're going to practice that a little bit. We're going to do a lot of predicting where points land, and really to remember the whole AB, and if you're rotating about the origin, will be very helpful. So make sure you've written that down. Good work.